This is Mrs. O'Neill for AP Chemistry, Chapter 1, Section 5, Uncertainty and Measurement. Your objectives are about observing sig figs to report them to the correct quantity and also to perform calculations mathematically and give the answer to the correct sig figs. Again, you might want to pause the video, fill in the blanks in your packet, and then play to hear my words. There are two kinds of numbers, exact, which those values are known, and inexact, which have some uncertainty to them. So what does this mean, uncertainty? All measurements have some degree of uncertainty, and this is where the basis for sig figs come in. So if we look at an example here, when we're reading this graduated cylinder, okay, we're reading the bottom of the meniscus, okay? So the 1.1 is the same through all of these three measurements. So those are exact numbers. Those are certain. 1.1, no matter who reads this graduated cylinder, it's going to be 1.1. It's the 4, the 5, and the 6. That's the degree of uncertainty. My eyes might see 4, your eyes might see 5, and somebody else's eyes might see 6. So that's the level of uncertainty. And if you take analytical chemistry, this is what you'd have to add to every single measurement, the plus minus 0.01 in this case, because this tool or this uncertainty is that 0.01. So it could be, you'd always go in the middle, and it could always be 1 or 2 after that. So let's look at a ruler. So in instance, no matter what, everybody's going to know that this is going to measure 2. Everybody's going to read that it measures 0.5. It's this guy that's uncertain. So if you look between these two rulers, this would have 3 sig figs because I can measure it to this second decimal point. But if we would measure using this ruler, we would only measure to 0.5, to that first decimal place. Because again, it depends on how the tool is used. So that's where sig figs come into play. But it's still always that last digit. You want to go that extra mile when you're making a measurement, because you want to make sure that that last digit is uncertain, but you still have to estimate it. Okay. So then there's a difference between precision and accuracy. Precision has to be repeatable. We want to remember that. And if you remember the video you saw with Mr. Anderson, he talked about precision and accuracy. So precision has to be repeatable. Accuracy is just, it's correct. Are you close to the true value? So in order for anything to even have some kind of precision to it, it has to have multiple measurements. So if you only do the measurement once, you're either accurate or not accurate. Precision doesn't even play a part in it. So let's look at these dartboards. So as you can see, our first dart, all of our measurements are hitting the area that we want. So we are precise because we're hitting it multiple times, and we're also accurate. But if we look at this dartboard, again, we're precise because we're hitting the area multiple times, but we're not accurate. And this is where error is going to play a big part. What kind of error would this be? Is it the equipment error? If the equipment is not calibrated correctly, it's going to give you that same error over and over again. This one now does not have any precision because the darts are all over the place. Now it's saying yes to accurate because of that just one shot, that one lucky shot that hit the middle. They can claim that yes, we're accurate. We hit it one time, because remember, accurate does not need multiple parts, but it does still need to get where we want to go. And of course, this one would not be accurate nor precise. So if we look at something like a graph or data, so again here, if we're trying to hit the line and all of our dots hit the line, then we have good accuracy and good precision. Here, however, if we notice, those dots are all over the place. So it's not precise, but it is accurate because we have 1, 2, 3 that are on the line. This one we have it good precision because we're hitting the same spot over and over again, but it's not accurate at all. We didn't hit the line at all. And this one again we have it's poor accuracy because technically I guess they're saying that there's only one here. I mean, we can still claim that it's accurate, but precision, no way. So again, depending on the data and depending on how many times you try to hit the target is going to depend on accuracy versus precision. So think of these things. Better precision implies better accuracy. So it's going to depend on the error. Is it equipment error, human error, those kinds of things. You cannot have accuracy without precision. So again, most usually if you're precise, so if we look here at the start thing, if you are accurate, this is what it's trying to tell you. If you are accurate, most likely then you're precise. But you can have precision without accuracy. So again, I can hit the same target over and over and over again at a same spot. So I'd be precise, but I'm not accurate because I'm not hitting the middle area that I want. So then let's talk about error. There are two kinds of error, random and systematic. So random has an equal chance of being high or low. So that's where we try to average the measurements. Where systematic means that it's the same all the time. So that's systematic is like being precise but not accurate, meaning that you're getting the same answers over and over and over again, but again, maybe your bad equipment or maybe human error or whatever is playing a part in it. That's the one you really want to avoid, because that means it seems like you're getting the right answers, but you're really not. So random is just, something happens kind of here and there all over the place. So we usually calculate percent error in our lab results because we want to know how far off we are to the book value or to the true value that's given to us. So now let's look at sig figs. And sig figs are digits that are known. So there's 4 rules that's in your packet that you can fill out, but I want to go over a memory hook. And I feel like this is the easiest memory hook that I have found to get us to be able to count sig figs. So here we go. So I like to look at the United States. We have the Pacific Ocean on the left and we have the Atlantic Ocean on the right. So we're going to say the Pacific Ocean represents the decimal point being present and the Atlantic Ocean as the decimal place being absent. So what do we mean by that? If the decimal point is absent, we're going to start at the Atlantic side. We're going to find the first non-zero and then count them all up. So we're going to go that way, right to left. So if we look at this number, I do not see a decimal place, so the decimal place is absent. So I'm going to go and go and go until I hit the first non-zero, which is the 3. So 1, 2. This would have 2 sig figs. Here's another example. Again, no decimal place, so I'm going to start at the Atlantic because it's absent. I'm going to start counting from the, lost my thing here, 5, 7, 1. So that would be 3 sig figs. So this is the easiest kind of memory hook I've found. So let's go the other way. If the decimal place is present, now I'm going to start at the Pacific and I'm going to work my way to the Atlantic side. Okay, so same thing though. The decimal place is present. I'm going to go to my first non-zero, which is the 4 in this case. 4, 5, that would be 2 sig figs. So let's look at this number. Again, the decimal place is present, so I'm going to start at the Pacific side, go till I hit my first non-zero, and start counting. 1, 2, 3, 4, 5. So this would be 5 sig figs. So in this case, those zeros would be significant. Okay, so that's the easiest way. Here again, you might want to pause the video, try to understand the information, fill in the blanks, and then play my words. Obviously, rule number 1 is the easiest. All non-zero numbers are significant. Rule number 2 is pretty easy too. If the zeros are in between non-zero numbers, those are also significant. And 3 and 4, I'm not going to go into great detail because those were the Pacific/Atlantic memory hook that we just talked about. So what do these numbers have in common? The 5, the 5.0, the 5.000. Well, they're all the number 5, okay? But which one was measured to with the most precise tool? Of course, the one with the most sig figs. So that's what the sig figs really are important about. What tool are we using? And it's going to give us more precise or more sig figs to our measurements. There are 2 types of numbers that have no sig figs. Those would be counting numbers. There's 12 eggs in a dozen. 1, 2, 3, we're counting them. Or definitions and conversions. So this is going to be a big thing too. When we are converting from one unit to another, those conversions do not count towards our sig figs when we are doing mathematics. So there are some practice problems. You might want to pause the video and then check your answers. And then sig figs and calculations, real quick, when you're adding and subtracting, your answer should be to the number of decimal places that is with the least number that you started with. And in multiplication and division, again, your answer is going to be rounded to the least number of sig figs that you started with. So let's look at an example of adding. We're adding these two numbers. I like to line up the decimals. Sometimes that's the easiest way to do it. Do the adding. Now, find the estimated number in the problem. So your last decimal would be your estimated decimal. So here we have 2 decimal places. Here we only have 1. So the answer must be rounded to the 10th place. We got to get rid of that last number there because we only have 1 decimal place in this number. Our answer can only have 1 decimal place. If we're multiplying, okay, so here's our answer. However, we have 4 sig figs in this number, only 2 in this number, so our answer can only have 2 sig figs. So our answer has to be 180. Yeah, sometimes you have to round up pretty high. It seems that way anyways, but is this number better to be 170 or 180? So you have to go by which way is rounded better, or sometimes the easiest way to do it is to make your number into scientific notation. Again, practice problems, pause, and check your answers. I always say the rule of thumb is go to 3 sig figs because on your AP exam, there's usually 1 point awarded to 1 problem, and they always give you 1 sig fig in both directions. So in other words, if the answer was supposed to be to 3 sig figs, they would still give you the point if you only give them 2 sig figs or 4 sig figs. So again, the rule of thumb is 3 sig figs. If you keep it to 3 sig figs, you should be fine. Okay, I expect some questions next time we meet.